right, what do we have? Pre-Lab 6 is open. One video, short, on paired data analysis for you to look at and do before labs. You have until tomorrow to address your exam questions, exam 1 questions. I'll stay after class. We might finish a little early like we usually do. You could certainly bring up a question then. Homework 5 is due at 5 o'clock tonight. And homework 6, which is already open, after today's class, we just have this one last example to kind of wrap up. Hey guys, we've started. You can try any of the questions out. So we always try to complete that material so that once the homework's available, you could attempt to look at any of those questions to work on. Exam 2 is in 3 weeks from today. We will finish the material for that exam in terms of what's covered by next Thursday class. So that gives you some good time to still digest all that material. All right, do you have a question or comment at all before we recap our last example and move to our 5th of 5 scenarios? Question or comment? What's that 4th parameter that we worked through quite a bit together on Tuesday? It was where we have maybe 2 measurements on the same person, a before and an after. Or maybe we have 2 measurements made on 2 separate people, but they were matched up to go together because they were both females of a certain age range with a certain medical history. And we assigned one to one treatment or one to the other. We measure something that's quantitative. That's one of the key questions you have to ask on exam 2 is, what's being measured? What's the response here? So you know if it's proportions or means. And then once you're in that right category, you'll be asking, well, how many measurements do I have? Do I have 2 sets of measurements or 1? There's a lot of discussion back there. If there's a question, I take it. If not, we have started. Once you decide proportions and means, it's a matter of what kind of data do I have? 1 set of data, 2? Right now we're dealing with data that's matched or paired. And then we go into today the idea of when we have 2 independent samples once again. But in our paired data scenario, the parameter of interest, when our response is quantitative, is a mean. It's the mean of the differences. We did 2 examples together at the end of last class. We did a confidence interval for the piano lessons to see if it helped to improve reasoning. And then we looked at the knob turning experiment, and that's where we sort of wrapped up. Paired data can occur in a couple different ways. On your homework 6, there's a couple questions that ask you to refer to this list. It's also in your textbook, and talk about what kind of background is leading to our paired data here. Did we have each person or item measured twice, either under 2 conditions or a before and after? Or did we have a putting of individuals or items together that go together, are matched or paired specifically based on other characteristics? So you'll be asked to identify which of those is the paired data scenario background for that homework question. We were on page 144, where we were looking through and analyzing this data on this knob turning experiment, where we had each person, each of the 25 right-handed students, being measured twice under 2 different conditions. One, how long did it take him to turn the knob? That was right thread knob. And the other, how much time did it take him to turn that left thread knob to make the indicator go the same distance. We were asking the question whether or not right thread knobs are easier to turn on average. And the response here, what am I measuring? Time. Time to move that knob a fixed distance. That's a quantitative response. So that's why I know it's means and not proportions. Are right threads easier to turn on average? Also an indication of means. Next Thursday, end of class, we'll play Name That Scenario. And we'll talk about looking at the background and just identifying the right parameter, and maybe is it a confidence interval or a test that we're doing. That's the best practice I can give you before exam 2. So that once you're in that right scenario, you can go ahead and use the formula and address the question. So we had hypotheses set up. I want to emphasize again that if it's a paired data analysis, I want to see mu d. Not what you're going to see later today, which is mu1 minus mu2. Two different means and the difference. That's going to be reserved for when we have independent samples rather than paired or matched samples, so we know the distinction. Also, the output will often give you some clues. Here it is saying it's a paired samples test that's being done. The average of the differences, where it was right thread minus left thread, was indeed negative, negative 13 seconds. That indicates that descriptively the right thread times were more easily able to be turned. Their time was lower on average, which is what we were hoping to look for. Our data came in on the right side of the direction in our HA that we were looking for. Our t-statistic indeed was negative. And I'm doing a lower tail test. That's what I want to come together. If those two things don't match up, then your p-value is going to be huge, because you were looking for small and you're sitting over here large, or vice versa. All right, so we did go through and do the test, if I recall. We pulled out our t-statistic. Our sample mean difference, d bar, is almost 2.9, 3 standard errors below 0. That's how small, away from 0, our sample mean sits. Our p-value here, we noted at the very end, is being provided for the two-sided test. And that's going to be the case with SPSS and any t-test that's provided to you. It doesn't know if you're doing one-sided or two-sided. It doesn't know if it's a lower-tailed or upper-tailed. So you have to decipher from that two-sided p-value what is your p-value for your test. Knowing that my test statistic is negative and I'm doing a lower-tailed test means I am going to just divide that p-value in half. Our p-value for our one-sided test turned out to be 0.008 cut in half, 0.004. And I believe we reasoned through that together as our very last note. You can draw the picture. Even if I don't ask you to draw the picture, if you sketch it and put the actual test statistic down and shade what is your p-value, you'll do the right thing. You'll either be shading just one little tail or you'll be shading a huge part, which means I've got to do 1 minus that instead. All right, our p-value is extremely small. What will be our statistical decision? Do we reject H0 or fail to reject H0? We will reject H0 at the 5% level, which is our significance level here. We reject H0. Therefore, our conclusion would be what? We have sufficient evidence to support that for the population of students represented by our sample. That's always a good statement to put in there. Then it's truly about the population that we're making our conclusion about. We have sufficient evidence to say for the population represented by our sample, what statement? Well, just go back up to the question, the way it was asked. Maybe you have to tweak that a little bit because sometimes the question just says, are right thread knobs easier? Well, we mean easier on average. It has to be about a mean. So represented by the sample, we have sufficient evidence to say that the right hand threads are easier to turn on average. And I can't fit it all in. My screen is cut off. Or you can say the average time to turn the right thread knobs is quicker, faster than that for left. Something about the mean or the average time or mean. All right, there's our conclusion. Now, in order to do this test, in order to do the confidence interval we did about the preschool children, we have conditions or assumptions. And those are things that you might be asked, not for every scenario, but occasionally to either state or assess. One of the questions here, part D, asks us to think about which of these might be an assumption in order to do this paired t-test that we just conducted. So what does it say? Should we circle that first one? The turning times for the right thread knobs are independent of the turning times for the left thread knobs. Is that an assumption? Here are the right thread knob times, here are the left thread knob times. Are they independent? What kind of analysis did we just do? Paired. These are not independent of these. That first one is completely dependent on that first one because they came from the same person. They aren't independent sets. If they are, then my pairing or matching is not very effective at helping to reduce variability and see apples to apples, oranges to oranges. This is not a condition. If it were, then I shouldn't be doing a paired data analysis if they really are independent samples. How about one of these other two? One of them, they both talk about normality, which I know is a condition that's needed. The first one says the turning times for those right thread knobs are normally distributed. And that last bullet says the difference in turning times is normally distributed. Which one? Top or bottom? Bottom. It's all about the differences. Our conditions are about the differences. Our differences are a random sample from the population of all such differences. That population of differences should have a normal model to describe that response. So it is the last one that we should circle. I don't require normality for the befores and normality for the afters, or the right threads and left threads separately. I require normality of the differences. So how many QQ plots would I make here? I could potentially make 3. One on the right thread times, because that's going to be one of the variables in my data set. One for the left thread times, that's the second column of data. And then there'll be that third column of data, the differences. And I need to make a QQ plot of the differences. I can look at the data individually if I want to. Maybe I want to come up with, since right threads are easier, what the average time for right thread knobs would be, and a confidence interval around that X bar value. Well, then I'll check the normality of that set of data, or reflecting that for the population. All right, conditions. Very helpful technique might be to think about those 5 scenarios once we finish that last one over a little bit today and next Tuesday. And for each one of those scenarios, write out the conditions for doing either the confidence interval or the test to have that to study from. All right, page 147. Moving on to the next big chunk from our formula card, that's all about 2 means. We have actually handled the independent sample scenario already. We did it for 2 proportions, P1 and P2. We had this same list for how independent samples can come up, but our response wasn't quantitative at that point. Our response was categorical, so we talked about the proportion who said yes in each sample to estimate that for the populations. So how do independent samples occur? Maybe we actually go and take independent samples separately from our 2 populations. Here's our population or listing of all males. Here's our population of all female students, and we can take random samples from each of those respective frames or lists. Or maybe it's that we took one survey of students, but we measured other variables that we knew we'd like to look at the results by those variables, such as gender or age or whatever it might be. And then that creates these 2 populations and supposedly 2 samples then from those respective populations. That's done quite often. Or in the experiment side versus an observational study like a survey, in the experiment side, your key idea is that the participants were the subjects randomly assigned to these different treatment conditions, in this case having 2 of them. And then you measure the same response for everybody, but they had these 2 different conditions or treatments. It's that random assignment that will lead to independence. Now, we did have randomization used in our knob turning example. We discussed that we should randomize which knob they do first. So there was randomization there, but not in terms of assigning them to one treatment or the other. Everyone still did both knobs. Our response is quantitative, so we're still going to talk about means. But now, because they are separate populations with independent samples from each, we're going to be looking at the difference between the 2 means, rather than the mean of the differences when it's paired. Got a couple examples in the middle of that page that your textbook references. How much difference is there in this measurement, weight loss, on average, for two different possible treatments? One is through a diet versus one which is through exercise. So they have diet or exercise as the two treatments. Each subject only has one of those two that they get randomized to. Within each, you're still measuring a weight loss, so there's a paired data there to some extent, but you're comparing the two sets of data separately. And I'm not sure why this would be an interesting research question, but how much difference is there between the mean foot lengths of men versus women? But it would be a two sample scenario. The parameter is mu1 minus mu2, two separate means and their difference. The estimate, well, makes sense, I hope. X bar 1 minus X bar 2. We use X bar to estimate mu. We use D bar to estimate mu D. We'll use two sample means and their difference to estimate the two population means and their difference. So what I have are 3 slides that are not in your notes coming up. They're just a background and getting us practice at, is this background with these two sets of data coming in, are they paired data or independent samples? So we can make that distinction initially. So we'll read through each. It's just a background. There's no data there. You can think about what the data would look like if it were put into a data set. And all you have to do is select, I think this is paired data, or I think this would be treated as independent samples. So the first one, the research question is trying to determine if average GPAs are the same for psychology majors versus econ majors. Addressed by taking random sample of 30 psych majors and a random sample of 30 econ majors, recording their GPA so we can compare those results. What do you think? Here's fine where if you want to check with your neighbor what they clicked in, I don't care. Think about the data, how it would come in. Oh wait, this is econ. All right, let's call it 5, 4, 3, 2, and 1. And the majority do have it. Here we would have independent sets of data. Independent sense, why? One of the things you can do is you can imagine what the data will look like. There'll be 30 GPAs under the psych heading. There'll be 30 GPAs under the econ heading. And then say, what if I circled those first two observations under each? First one here and first one here. Do they have to go together? Do they need to be compared directly together because they have something in common that they share? They're both GPAs, which all of them are, though. They share that with everything. They're both GPAs from students. That's, again, shared with everything. But is there anything that makes that top one have to go with that top one in the other column? No. Unless we measured and did it by, well, we want to make sure we control for what standing they are, freshman, sophomore, junior, senior. So you keep those going together. Or you control by gender or whatever it might be. But we haven't done that here. There was nothing in the description that said that was done. So we have independent samples. Here we would be looking at a mean for psychology compared to the mean for the econ majors, the mean GPA. We would be wanting to assess if H0, those two population mean GPAs are the same versus are they different? Probably a two-sided hypothesis test. I will have two separate means. I could write the H0 as mean for psychology being equal to that for econ, or what else could I write it as? The difference in those two means is 0 to identify sort of the parameter and this null value. Good. Independent samples, not match paired. You could always refine your technique to do some matching if you wish, if you thought that was important to do. But here, no indication of any pairing. All right, our next one. we're looking at pedestrians crossing an intersection, trying to determine if on average the number that cross the intersection is higher in the morning than in the afternoon. Here's what we do. We measure the counts, how many people cross, each morning and afternoon over a certain time period for 20 randomly selected days this coming month. That's what the data would look like. Give you 5, 4, 3, 2, and 1. Not quite as distinctive, but we are selecting the other option more often, which is paired. That's what it would be. Why is it paired? What is it paired by? What makes those first two observations go together?
Same intersection.
Not the same intersection, because they're all taken at the same intersection. They were made on the same day. There would be another variable probably in the data set that would be what? Day number 1, March 10th. Day number 2, let's do it on the weekend too, March 13th. We pick a few days at random and you do it on the same day. Why? Because if it's a Friday, it might be busier than if it's a Tuesday. And I want to put the morning and afternoon on a busy day together because they go together. If next Thursday, St. Patrick's Day, there's more people out there, well, then maybe we should put those observations together too. It'll be a higher volume on both, maybe morning and afternoon. So we pair by the day. There is something that makes those two specifically go together. They're both from March 10th, and the others are not. Not that they were both at the same intersection. That's just to have similar data. Of course, you're measuring the same thing, but at different days, different time points. All right. And we have one more, which of course then could be either one, since we've seen one of each. And that is about speeds of cars. Is the average car speed lower if a police car is parked on the side of the road than the average car speed if the police car is patrolling the area? So we'll take speeds for 25 randomly selected cars during a Monday morning when there's a police car parked. We'll also record the speeds for 25 randomly selected cars when it's a Monday morning, same hour, and the police car is patrolling. What do you think? All right, let's give you 5, 4, 3, 2, and 1. Reverses back, but still about 1/3, 2/3. And it should be the majority again, B. We're back to independent. Well, they're all speeds of cars. They were all taken on a Monday morning at some given hour, 2 different Mondays, but because you can't have the same thing happen at the same time. Along the same stretch of road, that's what makes it consistent and homogeneous to go together. But these are 25 separate cars from the other 25, and there's nothing that would put that first car's speed that I observed that first Monday morning when the police car was parked with that first car speed that I recorded that next Monday morning when there was a patrolling vehicle instead. All right? Independent samples. Often the sample sizes will be the same to have a balanced design. If they aren't the same, which can happen in this independent samples problem, then you know it's independent samples. Can have pairing if they aren't matched with numbers. But it would be two sets of data separately. Couple clues. There is also the word average, car speed under one condition, and another average, separate mean, under two, second condition. If instead of recording the speeds, I simply recorded for each car whether it was speeding or not, to look at the rates of speeding under those two conditions, then I would be comparing not two means but two proportions. A P1, the proportion of cars that were speeding under that first treatment, compared to P2. And that would be something you did back in earlier material. All right, so let's move on to the background for independent samples and how we analyze that data. How fast have you ever driven a car? That was asked of college men and women. And you've got a summary of some of those results. Top of page 140, yep, 54. What is that, 148? Males versus females. The average for the males, there were 87 males in this study, 107 miles per hour. The average for females, 19 miles less, 88. This little table that you have at the top of your notes is a very classic way of giving you data that's for two independent samples, because we've summarized the two separate samples separately. And there's no way you can recreate back from that table only any kind of D bar or SD, the differences. Wouldn't make sense here anyway because I have 87 separate males compared to the 102 females that were surveyed. It's not a matched or paired design. All right, so we want to learn about the difference in these two population means. We want to compare those two means for these two populations. How would I estimate the difference in the true means? Take my data and calculate the difference in the sample means. You calculate that difference and you get 19 miles per hour. So, same questions. We asked these on Tuesday. We've asked these now 4 times earlier. And we do it again here. Can anyone tell me how close our observed difference, which was 19 miles per hour, is to that true difference in the population means? Can anyone tell me? The answer to that is no. The primary reason why it's no is because you don't know mu1 minus mu2. That's the whole purpose of gathering data, to learn about it. I cannot say how accurate my one answer is. I cannot say if my one confidence interval has the true parameter in it or not. I can tell you about how accurate the process is that I use to get that estimate or that interval. That process is thought through by thinking, what if we repeated the survey again? We don't really repeat it over and over and over. We do sometimes repeat things over time to look at trends, but we don't do the same study many times. But we think about, what if we did? Would we get that same value for the difference in our sample means? Our answer there has always been, probably not. Yes, occasionally I'll see a 19 perhaps again, but it's going to vary. This is a new statistic, x bar 1 minus x bar 2. That's our new statistic. It is a random variable. It would vary from one repetition of this study to the next. Well, what about 19 miles per hour? Doesn't that look big? Or is that really big? It's hard to know without the standard error, with the right yardstick. And we want to then kind of understand then what could those values for the difference in our sample means be? What is the sampling distribution of this fifth statistic, the difference in our sample means? All right, so this requires us thinking back for a moment to that section 8.8 that we've referred to once before, and now we'll refer to it again, which reminds us that if you want to look at the difference between two things, the mean of the difference is the difference in the means, but the variance of the difference, and we have to work on the variance scale first, and then take it to the standard deviation, but the variance of the difference is the sum of the variances, if they're independent. So what did we learn back in our first encounter with an x bar? Tell me what the standard deviation of x bar looks like. You've got it right there in your notes. What is it? Sigma over square root of n. That's how a x-bar value would tend to vary from that true mean mu. So the variance then of x-bar is going to be what? Sigma squared over n. Sigma over the square root of n, square it, you get sigma squared over n. That's what a variance of a single x-bar looks like. We're going to have two of those. One for the first population of possible x-bar values and one for the second. So we'll put a little 1 for the first group and a little 2 for the second group. And we need to pool those together by doing the sum of the variances. So let's fill in our box there at the bottom. What if we have two populations? They're both normally distributed responses, quantitative. And we take random samples from each independently, calculate that sample mean x-bar for each one, and either we take a large enough sample size or we do have this normality condition. But what do we know about then the difference in these sample means? What kind of model or shape do you think it's going to have? As has been for every other statistic we've really focused on. Approximately normal, bell-shaped. And then most of the statistics we've dealt with are good statistics. They're unbiased. They're centered around the thing you were hoping to estimate. The difference in the sample means, well, their mean, the mean of the difference is the difference in the means. And the difference in the means for the two x-bars will be then mu1 minus mu2. The difference in my sample means will vary around the true difference in those population means. And now I need that standard deviation. The result says you have to work with the variances. So let's put the variances in first. The variance of the difference is the sum of the two variances. So I need the first variance. That's going to be a sigma squared over n. I'll put a little 1 there for coming from that first population and that first sample size from it. And then I need that other variance. So I'll have 2 as the subscript. It's just another sigma squared over n. There's the sum of the variances. How do I bring it back to a standard deviation? Big square root. That's very similar to the one you had for proportions, which had a p1 minus p over n and another p1 minus p over n, and combined it. There's the result we need that will let us do a confidence interval and a test. Well, not quite. I will know mu1 minus mu2 under an h0 being known. If h0's true, there's no effect, no difference, I know mu1 minus mu2 would be 0. But I won't know sigma 1 or sigma 2. I typically only have data when I'm doing the inference side, and if that's the case, I can't put in that true sigma, but I can put in the respective s's. And on top of your next page, you've got that final standard error, which has the s's in instead of the sigmas, which are things that you can compute from your data, so you can calculate that estimated average distance and use it. Here is yet another interpretation of this standard error, as estimating roughly the average distance of the possible x-bar values from their mean, which is the true difference, all the pieces. So we'll be using that quantity in doing our inference. So looking ahead, we have both confidence intervals and testing that we often want to do. Sometimes we're trying to estimate the effect. Sometimes we have a theory about the effect that we want to put to the test. So if we're doing the confidence interval side, with our basic structure for confidence intervals, best guess, plus or minus a few standard errors, and we're doing means, which we've done now twice before with a single mu and mu d. What do you know is the answer to that first question? The few is going to be some type of t-star value. Whenever it's means and you're doing a confidence interval inference or a testing of hypotheses, you will be doing t's. When you do have the knowledge of, let's suppose sigma is, the true standard deviation is known, well then you'd be able to calculate the corresponding z instead of a t and calculate some probabilities with that, but there was no estimation typically involved there or no hypothesis testing. But when we're doing the confidence intervals and the t-tests, we'll be working with the t-distribution. How about degrees of freedom? So far they've been what? n minus 1, because you have just one set of data. Now we have 2. So what will be the degrees of freedom for one group? N1 minus 1? That would be the degrees of freedom for that first sample that was selected. How about the degrees of freedom for the second sample? N2 minus 1? I need the total degrees of freedom. One form of degrees of freedom, the one that we'll prefer to use, because there's actually going to be 2 variations of this method, will be the one where I can combine the 2 sets of data and use the total degrees of freedom, which would then be what? N1 plus N2 minus 2. What do you think the degrees of freedom will be when we turn to looking at 3 groups? New treatment, standard treatment, placebo control. 3 different treatments we want to compare simultaneously. N1 plus N2 plus N3 minus 3. All right. On the confidence interval side then, we move to the testing. It's going to look like some standardized quantity, some test statistic. I won't be able to put a null standard deviation down there. I only will be able to put the standard error that I have. Whereas under proportions, we were able to put a P naught in that denominator, the actual null standard quantity. Question?
You said we used two-star value in this one because we didn't know the population standard deviation.
Right. Since the standard deviations aren't known, this kind of statistic that we would be forming here, which is what we unstandardize when we make a confidence interval, isn't going to be called a Z. So we won't be looking up some Z star. This is going to be called a T statistic. For means, you're going to be using T's. For doing confidence intervals and testing. For proportions, we'll require, if we can, a large sample size so we can go to the Z procedures there. But there is nothing in any of our T tests or T intervals that said you must have a large sample size. Or both of your samples must be both large, both more than 25 or 30. We never require that. That's always a nice feature of your study if you can, because then when you check the required condition of normality for your population and it doesn't look so good, you can fall back on that central limit theorem result, which does say you need that large sample size, but you don't require that to do the test initially. So it is a T statistic we'll be calculating. There actually will be two versions, depending on one other condition, if we can assume it or not. But what do you think will be the H naught that we'll write out almost all the time for this kind of scenario? Status quo. No effect. No difference on average. So the difference in the means is 0. There could be a value there. We can always modify our test accordingly, but that's mostly what we'll be testing. All right, I think my picture of the day is coming next. I've been putting a scrapbook together of Halloween costumes throughout the years. This is one of some friends of my daughter. They went as a BLT. I know I should have flipped it around, bacon, lettuce, tomato, with bread on the ends. That was a pretty cool costume, I thought. Very creative. Bread, BLT. All right. My daughter she has 5 other friends, and they call themselves the lunch buddies because they sit at the same lunch table in middle school there every single day from 6th grade. They did it in 7th grade now. They're going to do it in 8th grade, I'm sure.
High school gets all messed up.
I know, high school gets all messed up. But they meet, even though they're in different classes and different things, they always meet together for lunch. All right. And that was part of the lunch buddy crew. Here's what we have left today to do. We've got to get the formulas done first. So we're going to derive them and put them together. Then next Tuesday and next Thursday is all working with data and numbers and practicing. And we've got a handful of examples in this section because there's going to be 2 versions, 2 cases. Your textbook calls them lesson 1, lesson 2. And we've got to decide further which of those 2 do we apply. So we'll identify it's 2 independent samples. It's about means. But then we'll have one further question. Do I do this general or unpooled technique, which we'll derive first because that's most straightforward? Or do I do this pooled technique? Because one more thing could be assumed. Prefer if I can go to that route if I can, but if I can't, I've got this other. So we're going to lay out the 2 backgrounds today. Not going to see much more data or numbers. just more formulas, but then we'll work with those and we'll go through a checklist for each of the, about 6 examples we'll do together next week. So lesson 1 is the first and more straightforward case. It's the general, or what is called unpooled because the other one's pooled, where we have the typical data background. Here's your 2 data sets. You will summarize with the sample sizes. They may or may not be the same. You can have independent samples with not exactly a balanced design. We'll have our 2 sample means, of course, because we're trying to learn about the 2 population means. And I will likely give you those 2 standard deviations, so you don't have to compute them separately. Homework 6, you have 1 question, 5 pairs of mother-daughter measurements that you have to actually calculate the 5 differences and calculate the D bar and the S sub D, but you can do that on a homework. All right, so we already have laid out that if we're trying to learn about the difference in our population means, let's just use those 2 sample means and calculate their difference. And then here is that standard error that we already derived. So we already laid it out. Confidence interval should be best guess plus or minus a few of these standard errors. Slight problem when we use that approach here with this standard error. It turns out that with that standard error in the bottom of your standardized quantity, it's not even quite a t. It's close to a t distribution for what it has, but not quite. You can approximate the t distribution with a certain degrees of freedom, and there's a hard way of doing that or an easy way. So here is the basic confidence interval as we would calculate it after we get this combined standard error. We will use t star here and look up a multiplier from our table. We can use it with an approximation to come up with degrees of freedom, or if we're doing it by hand, a conservative approach. So there's this degrees of freedom with an approximation, and it's a formula that I don't even want you to see or look at. It's a footnote in your textbook. Very complicated. It's called Welch's approximation, and you get degrees of freedom out that aren't even whole numbers when you often calculate it. But it does give you a better approximation to the t distribution that you're using than the conservative approach here, which will often give you an interval that's wider than you need. So if you have output, you're going to just use the values from the output, and it will be doing this degrees of freedom using a Welch's approximation for you. If you are doing it by hand, because you just have your classic data set up, and that's all you've got for the data, you don't have it in a data set to have it do the analysis with SPSS, well then, conservatively, i.e. if you're doing it by hand, we'll take for the degrees of freedom the smaller of the 2 sets of degrees of freedom. So I have 20 subjects in one group and only 15 in the other. What will be my degrees of freedom if I'm doing it by hand? There's 20 and there's 15. That's 19 and 14 degrees of freedom, and I use the smaller one. So 14. That's the only thing I'll use, my t star. It'll make my multiplier bigger than I need to, but it's one safe way to do it by hand versus this kind of very complicated approximation. Here's the checklist for what the interval requires. A little bit more. There are 2 conditions about the data. Those 2 samples need to each be a random sample, and those 2 samples need to be independent, not matched or paired. You can put it together in one, independent random samples. But those are 2 separate conditions. So the independence is by the design of your study, how you gathered your data. The random samples is along that same lines of how you selected those subjects. And then, of course, the other one back on the populations, and there are 2 populations, is to have the normal model be appropriate for whatever you're measuring for both populations. The little clarifier here, which we've always adjusted to 25, but the large sample size is not a requirement, would not be in your list of here's what you need to do the test, but it's a helpful plus if the normality condition on your populations doesn't look that great. The central limit theorem can be that sort of safety net for you. And you have approximate results. There's the general confidence intervals, more straightforward. The second page we derive together the pooled case. So we already have the conditions laid out. Each sample needs to be a random sample, and they have to be independent random samples, independent. And the only thing I'm requiring right now on the populations is that they're both a normal model. If it's reasonable to assume that the measurements in that first population, they vary with about the same variability as those measurements in the second population, then I can do a pooled technique instead. Is it reasonable to assume that the measurements in your two populations have the same variance or same standard deviation? What would that mean? That would mean the variance in the first population would be equal to that measure of variability in those quantitative measurements in that second population. So if they are equal, I really don't have to have a 1 and a 2 subscript anymore, because there is just really a common population variance then. Now that's actually can be supported in many cases. I have a new teaching method, and I want to compare it to a standard one. And I'll be randomizing my subjects to two groups after a period of time where they're taught with those respective methods. You do some assessment. Those scores are measured. Student scores will vary. These scores will vary around whatever this true mean is, and these scores will vary here around a true mean. The variability being about the same is somewhat reasonable. And you can check that by looking at your data too, which will show you a little checklist to say, is this reasonable? But it does often be the case. So that the only thing that's different between my two populations then, they're both quantitative measurements, they both have the same amount of variability, but they might be around different means. And I want to know what those different means are and how they compare. So if we can assume this, and we'll have a little checklist for how to determine that, well then those two S's that we have don't have to be used separately. They can be pooled together. A more powerful estimate of this overall common variability. So how would we do that? Should I just take the two S's and average them? What if the first sample standard deviation or variance came from my study with that first treatment where I had 100 subjects, but over here I only had 50 subjects in that second group? Which of those two standard deviations would you probably have more faith in terms of being a better estimate? The one from the larger sample. So I want to weight them somewhat by their sample sizes. Give more weight to the estimate that came from the larger group if there was a difference. So here's what we'll do. We're going to derive this thing called the pooled standard deviation. I've got it on the next page. I guess I'll just show it to you rather than write it all out. You've got it there too, right? Right in your notes. Look what the weights are. What's n1 minus 1 and n2 minus 1? Those two things are called the degrees of freedom. So we weight them by the degrees of freedom, which is effectively like the sample size. We have to again work with variances. You have to pool things together by going the variances being pooled, and then you take the square root at the end. So here's the first sample variance, gets weighted by its degrees of freedom. And there's that second sample variance getting weighted by its degrees of freedom, effectively the sample size. On the bottom, you've got the total degrees of freedom. And that's what's always on the bottom of an S, the degrees of freedom. Your regular S that you calculate has sums of square things over n minus 1, degrees of freedom. Take the square root of that whole thing and you're back to a standard deviation. And notice we call this standard deviation with a little p subscript, which represents pooled. Pooling those two variability estimates together to come up with an overall more powerful estimate of that common standard deviation for the populations. So each sample variance gets weighted by its degrees of freedom. The larger the sample size, the larger the weight. The denominator really is the total degrees of freedom, somewhat what we highlighted earlier. Adding up the two degrees of freedom gives us this thing called n1 plus n2 minus 2. Adding up those total degrees of freedom. So instead of having a separate S, S1 and S2, in our standard error expression, we're going to use SP in both places. So now we need to derive the updated standard error. This is the updated standard deviation estimate, and in our standard error expression, let's put in the SP instead. So if we have our unpooled standard error, just as a frame of reference or starting point, what's the pooled one going to look like? Well, I'm going to put in for the unpooled standard error, not S1 and S2, but let's put in the SP squared in both places. That would be the better estimate to use instead of separately the S's. Because it would be okay to do that if the variances were really the same. And then I want to simplify it. So let's pull that SP squared kind of in front, and I'm left with the 1 over N1 and this 1 over N2. And I actually could simplify it one more way, right? Instead of having the square under the square root, let's bring it out front. So that's the way it's often summarized and the way it appears in your formula card. SP pulled out front, square root, and then that 1 over N1 and that 1 over N2. There's your new standard error. A little more complicated to get to it, but if you can use this in doing your confidence interval, you will be using an exact t-distribution with an exact degrees of freedom that will be larger and therefore better than the unpooled case, especially if you have to do it by hand. So you've got your box at the bottom, the final box. You have two boxes now in this scenario. This is the pooled version. If you look at your formula card, that takes up a big chunk of that second page because it's got the general and the pooled results. The pooled standard error needs to be used here. It requires one more step. To get your pooled standard error, you've got to calculate that SP separately. That takes a bit of work. We'll do it once next week with data ourselves, and we'll see the wonderful output that gives you the answer without having to calculate it. But the value that we look up for T star now comes from a t-distribution with that total degrees of freedom. N1 plus N2 minus 2 will always be bigger than the smaller of N1 minus 1 or N2 minus 1. This will be a more powerful inference technique. It'll give us an interval that's a little more exact if we can assume this equal population variance. There's the extra piece in this box compared to the other one in terms of conditions. I think of there being two conditions about the samples. They're put together in that one phrase, independent random samples. And then I think of two conditions about the populations. Here are two populations. What do I assume? The responses in each of those populations individually each has a normal model, but the variabilities are the same. I have a lot of students saying in this condition when they write it out on the exam, equal variance. What's the missing word that has to be there? Population. You're assuming the populations have equal variance. Because you're going to look at your data to check that, and your two S's sitting there from your data sets are never going to be the same, even if the populations did have equal variance, because that's data from random samples. You'll be looking at those two S's to see if they're comparable. Are they close? And we'll give you some guidelines for that as one check to see whether we can assume this thing about the populations. So make sure you are complete in your condition writing out. I have two populations that each have a normal model for my response, and those population variances are assumed to be equal. Or you could say population standard deviations are equal. That's equivalent. The sample sizes being large, again, still works for us if we need to fall back on that CLT. So your page 153 has a nice long list of guidelines. I think we'll reserve that for doing and then doing data analysis together on Tuesday. We're done.